Today, we're going to talk about, the lecture is entitled Applications of NLP, but what we'll really talk about are mostly information retrieval, information extraction, relation extraction, and question answering. All of these fit together in a nice package, and we're going to talk about them as a nice package. Can everybody hear me? So if I start speaking more quietly and you can't hear me, or if I'm not speaking slowly and clearly enough, then please raise your hand and let me know, because I want everybody to hear and understand what we're talking about today. The lecture today is an important one, and part of the reason that it's important is because a large part of your grade is a project. And today is the day when we'll speak about the background that you need to know in order to do your project. What the baseline system is that you would use to do the question answering part of your project. Not the question generation part, which we'll talk about next time in more detail, but the question answering part of your project. To start off, are there any questions of a procedural or other nature that should come before the class? Is everything clear from last time, from the website? Has everybody visited the website, looked at the syllabus? By the way, the syllabus says spring 2019, but everything on the syllabus but the date has been updated. So you'll notice the dates on the schedule are fall 2019. So please refer to that and to the policies, particularly the policies on intellectual or an academic honesty and basically cheating and collaboration. So this is important right now because the first homework has just been released. The first exciting homework. It's an easy homework. It's a homework on regular expressions and using regular expressions to anonymize some text. It's not hard, but it's important because we want to make sure that, and there's also a substitution cipher that you have to figure out quantitatively. And we want to make sure that you have the basic skills necessary to do these kinds of things before we unleash more complicated NLP kinds of tasks on you. So this is like, if you find this difficult, you may want to put this class off and do a little bit more computer science before, and have a little bit more coding experience before you do this class. But we think that most of you, in our experience, almost all of you will find it pretty easy. So the assignment is up on Gradescope and up on Piazza. Is that right? Is that where we're posting the write-ups? Is this shown here? I guess he's not. It's where Piazza says it is. Where the homework's posted? Piazza. It's already been posted. Okay. So go do that. Yes?
For people who are registered late, how can we get access to Piazza?
We will add everybody again to Piazza today after this class. So if you're registered, you'll be on Piazza. If you're not registered and you still want to be on Piazza because you think you're going to get registered soon as you straighten out conflicts, email us and we'll add you to Piazza as well. Yes?
It should be possible for you to just add yourself unless you have a sentence set up that please scan themselves.
We don't do it that way, actually, but for various reasons. We could do that, or use a code, but basically, we don't want random people adding themselves to the class. Any other questions about that? Okay, let's talk about applications of NLP. We're going to start off talking about information extraction. This is a class of tasks. And these are tasks basically where you start off with an empty relational database. You start off with an empty table. And then you try to populate this table with information from text. So one kind of thing that you might, so if you have a relation of state, party to candidate to fraction in some kind of polling or voting, this would be a kind of relation that you might have in a database. The goal in information extraction is to go and fill this in, to go fill in that table given text. Now, there are all sorts of variants of this because there are all sorts of different tables that you might want to fill in. Excuse me, I have to make sure this is recording. Yeah. Sorry, I just had a scare that I didn't press the record button before I started talking. So this is information extraction from a distance. And there are all sorts of different things that you might want to extract. But anytime you're taking unstructured textual information and extracting from it structured data, that's information extraction. So one kind of information extraction task, in fact, my favorite information extraction task is named entity recognition, or NER for short. So a named entity is sort of like a proper noun. It's a name in text that refers to some entity in the world. And typically, in named entity recognition, we have a subset of possible names that we're concerned about, like the names of persons, of organizations, of locations, of geopolitical entities, maybe just those four, or maybe also natural phenomena like hurricanes that we give names to, or facilities like dams or factories. So, but usually we're just interested in some proper names that have certain types. And we identify where in text these occur. What spans within text correspond to a name that fits in one of these categories. So in this example here, you've got Senator John Edwards. This is from olden times, an election long ago in the United States, when 3 Democratic candidates were Senator John Edwards, Senator Hillary Clinton, and Senator Barack Obama. And this is talking about their performance in Florida, the worst U.S. state. In the Democratic Party primary. So we've got Senator John Edwards. That's a named entity. It's a person. Democratic Party also is a named entity. It's an organization. Florida is a named entity. It's a geopolitical entity. Edwards, again, is a name of a person, named entity. And Hillary Clinton and Barack Obama also are names of persons, therefore they're named entities. So named entity recognition is the task of finding all of these and labeling them. So we find that it's complicated by the fact that not all names of, let's say, a person are identical strings. So both Senator John Edwards and Edwards refer to one entity in the real world. This guy, so it's sometimes difficult to just list all of the names that you're interested in. You have to do something more sophisticated than that. And often you're not just interested in the names themselves. That's the first step. You're interested in how they relate to one another. For example, which names refer to the same entities. And this is a task that's called co-reference resolution, where you form chains that link the instances, the mentions of the same entity together. So that Edwards gets linked to Senator John Edwards because they're the same entity. They're mentions of the same entity. That's co-reference resolution. Now you can have co-reference resolution that's not just between names. You can have co-reference resolutions also commonly with pronouns, where it's like he or she or it or I or you. These can also be co-referenced with names and other entities or entity mentions. And we'll talk about this later on when we talk about discourse. But for now, let's just think of co-reference resolution as being resolving the co-reference between names. So you might be interested in the names themselves. You might be interested in how they connect to each other. It may be more interesting to think about relations between names. So you might have a member of relation. And it might be useful to be able to read through this text and to be able to say that there's a member of relationship between John Edwards and Democratic Party, or between Barack Obama and Democratic Party. That's relation detection or relation extraction. So those are three kinds of information extraction. Let's talk about NER first, because it's my favorite. So the NER problem is what is called a sequence labeling problem. If you look at the column here, you'll see we have a sequence of words. The task is to attach a label to each word in this sequence that says whether it is outside of a named entity, at the beginning of a named entity, or inside a named entity. And it specifies the type of that named entity. So as we go through here, we have President Donald Trump met with local leaders and federal responders shortly after landing at an Air Force base in Carolina, Puerto Rico. Carolina and Puerto Rico. So President Donald Trump is the named entity, right? It's a person, name of a person. So sometimes titles like president don't get included. It depends on what kind of named entity recognition you're doing. But for our purposes, let's say that it's part of the name, the President Donald Trump. So because president is the first token, that's like the first word, in the sequence, then it gets this B per tag. Then Donald Trump, each of these tokens is within the named entity, but is subsequent to the initial token. So they get an I per tag, showing that they're inside the named entity, but they're not initial. They're not at the beginning. Then everything that's not in a named entity, all of the tokens that are not in a named entity get an O for outside. The Air Force is an organization, so the first token gets a B org, the second token gets an I org, and so on. So this kind of notation that is commonly used in named entity recognition is what's called BIO or IOB notation. There has to be two names for everything. It's actually a requirement among academics that every concept have at least two names, and that they be subtly distinguished, or that there be some political ramification to using one versus the other. I call it BIO because it's easy to remember. It's like bio, and it's beginning, in, out. But some people call it IOB, in, out, beginning. Why is beginning at the end? I don't know. So this is the problem in NER. You're given this sequence of words. You try to come up with a parallel sequence of labels. How would you do this? I can't hear you. So one thing is to use orthographic, that means writing system, features like capitalization. So in English, we capitalize the first letter of proper nouns, and that provides a really good feature for named entity recognition. So that might tell us that we're in a named entity. Will that tell us what type the named entity is? So that will give us like B and I. Yes?
You could have like dictionaries of different concepts. So persons like President Donald Trump and locations like Carolina, Puerto Rico.
So these are called gazetteers. You could have collections of words and their types, and of names and their types, and these are called gazetteers. So this is one thing that can be used in named entity recognition, is you can check and see if something is in the gazetteer. Yes?
You can use grammatical classification, like for example, if the words for in
Uh-huh.
location.
Yeah, so you can use indicator words. You can use features that are based on words in the context, like prepositions or titles. You know, if something starts with Mr. or Mrs. or Doctor, usually it's a name of a person. So there are different kinds of indicator words that you can use as features. So what kind of model might you use? We haven't talked about this yet, so this is sort of an unfair question, but I want to get you thinking. How would you do it? So you've got these features, gazetteer features, orthographic features, indicator features. Yes? Uh-huh. Okay, so you probably want to proceed through the data in order and perform some kind of processing that identified these spans using the features. Can you be more explicit than that? What do you think? Yeah.
I mean, it's like President Donald Trump. There's a president of multiple countries, so the word president is ambiguous. So maybe the longest string of labels that would fit a labeling dictionary would be the best heuristic for it.
Okay, so you could use longest common match,
Yeah.
or longest match in the gazetteer as a way of doing this. Any other thoughts? How do you incorporate the features, the other features, with the gazetteer features? Because you can't just use the gazetteer, because you're going to come across named entities that are not in the gazetteer, right? So what are you going to do? Okay, a neural net. What kind of neural model might you use? So there are lots of different architectures. Would you want a convolutional neural net?
You want to recurrent?
You probably want a recurrent neural net. So people often will use LSTMs for this. But there are other non-neural models that people use as well. So people use conditional random fields, or CRS. Historically, people have used hidden Markov models, which we'll talk about, and have also used other types of classifiers like SVMs, as part of a sequence labeling kind of paradigm. So here are some kinds of named entities. Different, depending on what you're doing and using named entity recognition for, you'll use different types. But these are the most common ones. So there's person, organization, location, geopolitical entity, facility, natural phenomenon. So the hardest thing here is the distinction between locations and geopolitical entities. So what is a geopolitical entity? What? So a capital is an example of a geopolitical entity, but it's a very specific example. Yes? So the name of a country is a geopolitical entity. The name of a city is a geopolitical entity. In fact, anything that has a government, a population, and an extent is a geopolitical entity. And anything else that's geographic is a location. True story. Well, how would you evaluate an NER system? It turns out that you do it using a kind of evaluation that you use for a lot of NLP tasks. And that is, you calculate precision and recall, and then take the harmonic mean of precision and recall and get a metric called F1. So what is precision and what is recall? There are definitions up here, but can somebody give me an intuitive explanation of what precision is? Yeah.
Recall would be how many of the total named entities you want to recognize that you captured.
Uh-huh.
And precision would be how many of the entities that you captured are correct.
Yeah. So in other words, that's right. So in other words, precision penalizes false positives. And recall penalizes false negatives. So precision is how pure kind of are the things that I classified as being relevant. And recall is like how thorough, how much did I actually get? How few things did I miss? So these are competing metrics. Usually, not always. Sometimes you can suck at both precision and recall. None of you will do that. That's other people. People who go to MIT, for example. They're actually terrible with both precision and recall. So this is the metric that we would use for basically any classification task. And although you might not notice it at first, sequence labeling tasks are classification tasks, because you're classifying each of these tokens, each of these words, into a small finite number of categories with labels. So who here has worked with precision and recall before? Quite a few of you. Yeah. So what about F1? There are other F metrics, but what is F1? Who here has worked with F1 before or used scores that were stated in terms of F1? Yeah, what is F1? Oh, we have in front first, and then there are two people line of sight. What did you say? Yeah. So it's a harmonic mean of recall and precision. So in other words, it equally weights recall and precision, right? So, so there are other F measures that weight one above the other, but the most commonly used single metric for a classification task is F1, which weights them equally. So here's how you build an NER system. Typically. There are other ways of doing it, but this is a typical way. So you start off with a big collection of documents. You take these documents and you pay some poor person to label all of the named entities in all of these documents. This becomes your training data, these annotated documents. So this is a problem because your system is only going to be as good as your annotations, and your annotators are poorly paid. So basically, your system, from the very beginning is doomed. Just kidding, kind of. So you've got your training data here, your annotated documents, and from that, you extract features, like these orthographic features or gazetteer features or indicator features, and encode everything in terms of IOB. So you've got a table, and it's empty right now. You think that everything is outside of a named entity. So that's your training data. Then you train classifiers to perform multi-way sequence labeling. Things like CRFs or SVMs, or you can use an LSTM to do this. And that's your NER system. The model that you get from this training process is the NER system. But it's not done yet. Because you have no idea whether your NER system is good or bad, whether you chose the best features, the best classifier. So you go here with some of your annotated documents that you held out, you didn't train on, and you test to evaluate precision and recall. This test data, and you use it to evaluate the system. Then what happens when your system sucks? So you have an iterative process where you try to figure out, well, is this a problem with feature engineering, which is less a problem if you use like an LSTM, or is this a problem with what architecture I used? And you iteratively do this until you're satisfied with your precision and recall. Does that make sense? So let's talk now about relation extraction. This is another kind of information extraction task. Here are some examples of relations you might be interested in. Affiliations, like being a married to or mother of, spokesman for, president of, owner of, inventor of, producer of. There are also geospatial relations, like to be near, to be on the outskirts of, to be southeast of, or part of relationships, like being a unit of, a parent of, annexed by, or acquired by. These are all relations. And here, we have these stated in terms of the types you might use in named entity recognition. So person-to-person relations, person or organization to artifact, that's what ART stands for, org to org, GPE to GPE, relations. So how would you go about extracting relations? Let's say you're interested in the married to relation. You're interested in, you have a corpus of text and you want to find all of the people who are married to someone else. You know, all of those pairs of where X is married to Y. All of these tuples. Or tuples if you're a barbarian. So how would you do this? Yes?
Label your sentences per word style. For example, you look at the subject of the sentence that contain married to.
Uh-huh.
Could be one part of the pair.
Uh-huh.
And you look for something.
So you could look for things that are in a particular syntactic relationship to each other, like subject and object. And let's be simpler than that. Is there a simpler thing that doesn't require us to look at syntax that we could use?
Instead use the last name instead of the last name because kind of consider
Well,
relevant to the last name.
we could use that as a feature. However, I have the same last name as my brother.
Yeah.
I'm actually not married to my brother. Lots of people in Korea have the last name Kim. Many of them are not married to each other.
Well, use that with Mr. and Miss or something like that.
Right.
In the same sentence. You find another indication. It'll be easier to use.
Yeah, you could use that definitely as a feature. But can you think of any other things places you could start? Yes. Okay. All right. So you could think about keywords that might occur with those two words that might indicate that there is such a relation between them. You might start with fixed phrases like X married Y or X is married to Y, kind of templates, right, based on keywords. Yes? Uh-huh. Yeah, so that actually would be a good first step to do NER and use it to identify persons and then exclude from the whatever you do next anything that doesn't, any entity that is not a person. So let's talk about a simple way of doing, a simple and somewhat noisy way of doing entity or relation extraction. So you start off with two things. You start off with tuples, and you start off with templates. Tuples of people who are married to each other, and templates, patterns that suggest a relationship of marriage. So if you have Brad is married to Angelina, Bill is married to Hillary, Hillary is married to Bill, Hillary is the wife of Bill, what tuples would we have there that correspond to the married relation? What? Ordered, yeah. Well, no, it's unordered in this case, actually. Typically, it would be ordered, but in this case, being married is reciprocal. So if A is married to B, B is married to A, typically. Who is married to whom? That's what we're asking when we say, what tuples are there that we could start off with? Brad and Angelina, Bill and Hillary. And what seed templates could we start off with? Is married to, is the wife of, is the husband of. So basically, we can find all X and Y where these templates exist, and we can extract the X's and Y's and find more tuples. Then we can do something clever, which is we can use those tuples to identify additional templates. So if we find that a lot of times one of these tuples that we find, they occur together in some span of text with some other pattern, with some other words, we can extract a template based on those tuples. Well, so we can feed in both tuples, seeding tuples, and seeding templates. And we end up with a kind of bootstrapping approach to relation extraction. So we have seed tuples that are added to our tuple set. Then we search for tuples. Then we extract patterns based on those tuples. Those are added to our pattern set, along with any seed tuples or seed patterns we started off with. Then we search for instances of those patterns and use those to extract tuples. We stick all of those tuples in our tuple store, and we continue to go around the circle until we have found all of the patterns and tuples in the database, or in the corpus, in the collection of text. So what problems do you foresee? Yes? Uh-huh. Yeah, so everybody who is coordinated with somebody else with and is suddenly married to them. So you'd probably want to use some things to stop this, like a stop word list that would prevent you from making templates that just consist of stop words of common words like and. But even so, you're going to end up with some templates that sometimes occurred with. So there's more than one relation that can occur between two married people than being married. That didn't come out quite right. But basically, just because they're married doesn't mean that every co-occurrence of those two names is talking about them being married, right? So it's going to be kind of noisy. But a lot of techniques are kind of noisy. And so is it going to be high precision, do you think, or high recall, or neither? Yes. Probably going to be high recall, but low precision. So let's talk about information retrieval. So let's say you want to build a search engine. And you want people to be able to type a query in terms of a sequence of words. And you want to retrieve all of the documents in a store of documents that are relevant to that query. How would you do this? Yes? Okay, so basically you could look for shared words between the query and the document. we're going to talk about a more sophisticated way of doing that. So the key to this is understanding that everything is a vector, or everything is best represented as a vector. This is actually not true. Like, if you really love someone, I don't suggest handing them a vector. They probably won't get that. You know, it's sort of hard to interpret. Unless they're a really geeky person, and then they might figure out what each of the dimensions mean, and it might really touch them. But vectors are really good for representing a lot of things. And so imagine each document in your collection is a vector. And then imagine your query is a vector. What can you do with vectors? Well, you could multiply them together. What else can you do?
Use different distance measures for them.
You can compute the distance between the vectors, right? So there are different distance measures between vectors. What are some distance measures between vectors? Yes. There's cosine similarity. There's Euclidean distance. There's an easy one. Dot product. Yeah.
Your document is probably going to be longer than the query. You could do something like a convolution.
Okay. That's true. Although we're not going to talk about that yet. But that's true. So the idea here is to represent each document as a sigma-dimensional vector, D1, where sigma is the number of words in the vocabulary of the corpus. And you represent the query in the same way. Actually, in real life, sigma would not be equal to the number of dimensions. The dimensions would not be the same as the number of words in the vocabulary, because we would do something more clever. But just bear with me for a moment. So we can then take the cosine similarity between the query and each of the words or each of the documents in the corpus. And we can choose the documents that have the highest cosine similarity. And we say that those are relevant, or more relevant than the other documents. So this is a clever way of favoring, it's a kind of what's called a bag of words approach to information retrieval, where the query, basically a bag of words. It's a vector that represents the words in the query. And the documents each have their vector representations, and we can use a similarity metric to compute the similarity between these vectors. In real life, often we'll do things like TF-IDF weighting, which is something we'll talk about a little bit later. But basically, this means you put greater weight on words that occur frequently in documents, but infrequently in the corpus. So if you have two words that are shared by the query and a document, that word matters more if it occurs in the document a lot or if it occurs in the corpus little. If it occurs few times in the total corpus. So it's an intuitive notion that that words should matter more. They should be more informative if they're more distinctive. So if you're searching for dogs and elephants, then we can assume that and occurs a lot in any of the documents, but it also is very frequent in the corpus. Dogs is sort of in the middle. And elephants, we can probably assume, is going to be relatively infrequent in the corpus. But in particular documents that are about elephants, then it's going to be more frequent. It's going to be more sensitive to the topic of those particular documents, and therefore more informative about the relevance of those documents to a query. Does this make sense? Okay. That's confusing. I'm going to skip it. So let's move to what you've all been waiting to hear about, and that's question answering. Because your project is half about question answering. And we're going to tell you, give you the baseline system that you need to understand, that you need to beat in your projects, okay? So here it is. We start off with a question. We process this question to make a query out of it, probably by converting it to a vector representation, and we classify it because we want to know what kind of a question it is. Is it a question, a who, what, where, when kind of question, or is it a yes-no question? So we want to classify the question and keep this information for later. Then we have a whole bunch of documents. We want a way of indexing these documents so we don't have to go and do pairwise comparisons exactly. And we use these indexed documents to do document retrieval. So we find the documents that have the highest cosine similarity to the query. So that gives us these documents here. Then we look through those documents. We divide those documents into passages, like paragraphs or sentences. And we find those sentences that have the highest cosine similarity to the query. So we end up with some passages. And we assume that the answer is in those passages. So we have some way of processing those passages to extract the answer. And we use information about what kind of question it was in that processing. So this might be syntactically informed, or it might be sort of dumb. You know, there are different ways of doing it. But basically, that's what this step refers to. And what you get as the output is an answer. Hopefully the right answer, right? Does this make sense? So this is a pretty common sense kind of flow that you might follow when you're developing a question answering system. In fact, what you'll be asked to do is a little bit simpler, because you won't have to do the information retrieval step where you have a whole bunch of documents, and you figure out which document is relevant. You'll already be given the document that's relevant. And your job only is to retrieve the passage, process the passages for the answer, and give back the answer. But your project has another half, which is answer or question generation. So given a document, you have to be able to produce questions. You have to do both question generation and question answering based on one document from Wikipedia about Pokemon. Just kidding, we've already done Pokemon, so probably won't be about Pokemon. So how do you tell whether your question answering system is good? One way of doing this is with the metric mean reciprocal rank. So the formula is given right here. The basic idea is, what you're asking is, on average, how far down in the list of results do you have to look before you find the right answer? So if your system is generating a list of answers, how far down in that list of answers do you have to look before you find the right answer on average? Ooh, we're way early. So these are some general tools that we've talked about this time, that we've invoked, that will come up again and again in applications of NLP. One is supervised classification. So what is supervised classification? What do we mean when we, I mean, this is basic, but what does the supervised mean in the context of machine learning? Yes. Yeah, you start with labeled data, labeled inputs that you can train on. So this is one type of classification, supervised classification. And we'll have a whole lecture on classification. In fact, I think two. One on traditional machine learning models of classification, and one on neural classifiers. And both of these, all of these have their place. There's some applications where an older classifier, even a naive-based classifier or an SVM, performs as well as a neural classifier, particularly in some low data situations. But supervised classification is an important thing to know about. And this came up when we did named entity recognition. It also comes up elsewhere. What is the opposite of supervised classification? Unsupervised classification. And what is unsupervised classification? What's another name for that? Clustering. Clustering. So this is also useful, but it's not typically what we would use for sequence labeling tasks in most situations, because we would assume we had labeled data. So another thing is feature vector representations. So this will come up again and again. It's very key to modern NLP. We represent everything as vectors. Sometimes the dimensions of these vectors correspond to particular interpretable features, like the frequency of a particular word. But often, particularly when we're talking about neural nets and word embeddings, and these vector representations will, there's no way of knowing what the individual dimensions mean, right? The nice thing is we can just abstract over all of them and think of them as vectors and treat them as vectors, and we don't have to worry about what anything means. We can just worry about how well they work. So bootstrapping. When did bootstrapping come up? When did we use bootstrapping in this lecture? Your what? In relation extraction. So bootstrapping techniques are important, and they're used in a lot of places in NLP. What makes a bootstrapping approach bootstrapping? Yes.
You could start out with your own self-made examples where you have those relations, and after that you can search for those in the corpus.
Yeah, so the idea with bootstrapping is that you start off with a small number of labeled data or a small number of seeds. And then based on those seeds, then and an iterative kind of process, you build a data bank of more, in the case of information, or in the case of relation extraction, more tuples and more templates, more patterns. So there are other more sophisticated kinds of bootstrapping, but this is a way of introducing the concept of bootstrapping. And you should all be familiar with it. In fact, I have been known at some points in the past to ask an exam question where you have to describe a bootstrapping approach to relation extraction. This may show up as an exam question. It might show up on a quiz. This is a good thing to know. In fact, all of these things are things that are fair game for quizzes and exams that we want you to know. Another thing is evaluation. You better know this. This will come up again and again in various forms. So, it's no good to build something if you can't know how well it works, and you can't know how well it works without some kind of evaluation metric. What is precision and recall a good evaluation metric for? I heard it from somewhere, but I think, or I hallucinated it. Yes. It's for a model, but what kind of model? Classification. So the basic paradigm is classification. Now, it turns out that there are all kinds of tasks that are basically classification tasks. So it's actually used very widely. And you should definitely understand what precision and recall are and be able to reproduce the formula. And you should also know what F1 is, and that F1 is the harmonic mean of precision and recall. So also mean reciprocal rank. What is mean reciprocal rank a metric for? For what? For information retrieval tasks, including question answering. Okay, so any questions before we bring things to a close? Who looked at the homework when they were supposed to be listening to the lecture? What? Oh, it's locked till 4:20? Oh. Well, in that case. So I don't know if you checked whether you get points for being an overachiever or whether you get penalized for not listening to lecture, but I suppose it's better than like WeChat or Facebook. Anyway, take care. Good luck with the homework. Pester the TAs. Go to office hours, etc.